Welcome back, students. I hope everybody went through the first video and came up with some solid understanding on what to accomplish in the final two sections of chapter 6. A lot of geometry and a lot of applications. Now let's actually move into one of the two sections here. The law of sines, section 2 of this notebook, which corresponds to section 6.5 of our textbook. It goes like this. Given triangle ABC, where capital A, capital B, and capital C are regarded as the size of the internal angles, and small a, small b, and small c corresponds to the length of the opposite side of those angles. In order to emphasize those oppositeness, I color-coded my picture here. Small a and capital A are in blue, small b and capital B are in red, small c and capital C are in green. And of course, this picture is actually randomized. So if you run this program many times, you get different pictures. But no matter what triangle you get, this identity remains the same. That's remarkable. Sine of capital A over small a is equal to sine of capital B over small b, and in turn it's equal to sine of capital C over small c. Now we're going to prove it, but we're going to do that at the end of this video. I'd like to postpone it as much as possible, and instead we're going to talk about the application first, at least elementary applications. That is this one. This is the most typical case that we have to use the law of sines. What do you mean by solving a triangle? That means find out all the angles and sides. Here, all three angles are given and one side is given. We have to find out the other two sides. Wait a minute, did I say all three angles are given? This problem gave me only A and C. How about B? Well, you can easily find out B because the sum of the internal angles of a triangle is always 180 degrees. So if I subtract the A and C 20 and 25 degrees away from 180 degrees, what do you get? B is equal to 135 degrees. So B can be easily calculated from the other two angles. So the situation, you can call it all three angles are known. Now all three angles are known, which means in this law of sine, all the numerators are known. How about the denominators? One of them is known. C is known, 80.4. So consequently, the last fraction, sine of capital C over small c, is completely known. What we are going to do now is to pair up this known quantity with one of the unknown, and then find out the remaining one variable, and then pair it up with this known quantity with the other fraction, and we can find out small b. Well, from the first equation here, we know the numerator, all the angles are known. The right hand side is completely determined. What's unknown is the denominator, small a value. So one equation, one unknown, just linear equation, you can easily solve it. Solve it, and you're going to get this quantity, and just plug it into your calculator. Make sure your calculator is in degree mode. You're going to get this length, 65.1 unit approximately. You can do the same thing to the other side. Sine of b over small b. The numerator is all known because all the angles are already determined. And this quantity here, sine of capital C over small c, that part is completely known. So finding out this b is no big deal. It's just a linear equation. Solve it, and then use your calculator to compute it out. Make sure your calculator is in degree mode. By the way, this problem came from our textbook. Is it here? The next page? Yes, it's here. Example 2. Figure 5 corresponds to the problem we just did. 20 degrees, 25 degrees, 80.4. We are looking for small a and small b. Even without the picture, we were able to do the problem rather easily, so I didn't bother drawing it. Now, the next three types of problems are, well, pretty much all the same, as a matter of fact, in terms of the setting. Small a and small b, two sides are known, and one end angle is given. Two sides are known, and one end angle is given. Two sides are known, and one end angle is given. Only the numbers differ, but the setting is identical. Let me show you the picture. I think it's this one. Yes, example 3 corresponds to the next problem we have. Capital A, the angle is 45 degrees, and small a is 7 square root of 2, and small b is equal to 7. Now, if the angle in between had been known, in other words, if the angle capital C had been known, this would have been a completely different story, because, well, in that case, we do not have the complete fraction known, so the laws of sine will fail, and we'll have to use law of cosines. We're going to discuss that issue in the next section. Let's go back to the problem. Capital A is known, and then small a, its opposite, is known. So in the law of sine, the first fraction is completely determined here. And we're going to pair it up with an unknown quantity, and small b is known, and we can find out the numerator. Let's do that. Setting these two up, capital A, small a, everything is known. Small b is known, so all you have to do is to find out sine of capital B algebraically. Not difficult. We can solve it. Turns out sine of capital B is 1/2. Now, what kind of angle gives you 1/2 upon taking the sine? 1, we have 30 degrees. 2, we have 150 degrees. Actually, let me remind you of sine equation. One solution is coming from arc sine. And once you have an arc sine, pi minus of that, or in terms of degree, 180 degrees minus that is also a solution. So when 30 degrees, the other candidate is 180 minus 30, so 150 degrees. Now, when b is 30 degrees, what is the third angle? You can find out easily by subtracting the sum of the other two angles from 180 degrees. This is bread and butter. Sum of the internal angles of a triangle is always 180 degrees. So if you know two angles, you can find out the third angle easily. What do we have? We have 105 degrees. Good. Yes. How about the second case? Subtract the sum of two angles from 180 degrees. What do you get? Negative 15 degrees? That doesn't make sense. We are talking about geometry, so everything has to be positive. So in this case, we don't have triangle. That's no. Consequently, B has to be 30 degrees, in which case C has to be 105 degrees. We have determined everything now, so all we need is small c. You see, the numerator is also determined. This one is unknown. Set it up as the original fraction we know. Okay, go ahead and do that. So for small c, algebraically solve it and then plug into calculator. We get 13.52 units or something like that. Next, let's do something very similar. Identical type of problem. Two sides, small a and small b, are given, and one of the end angle, a, is given. Setting is the same. The answer will look very different, actually. The method will be the same because this quantity is completely determined, and this quantity is known, so let's find out for the numerator sine of b. That's what we did over here. And sine of b turned out to be 0.912255. So capital B we can find out by taking arcsine. We ended up with about 65.81 or 65.82 degrees. In that case, you can find out the third angle by subtracting the sum of the other two angles from 180 degrees. What you get? 71.08 degrees approximately. Now, is that all? Well, there's another. 180 degrees minus 65.82 degrees is always a solution, because, you know, if you have y equals the sine of x, something like that, then you get a solution from arc sine, but pi minus of that is also a solution. In DMS measure, it's 180 degrees minus that. So B is 114.18 degrees. Do the same thing. You can find out C value, but this time this is valid angle, 22.72 degrees. So what we have, B is 65.8 degrees and C is 71.1 degrees. With these two, we can find out small c value. Everything is known except for c, so solving it, we get, well, this value. Case 2, B is 114.2 degrees and C is 22.7 degrees. Everything is known. This is known quantity. This one we just found out. So small c we can find out. Turns out this value. We have two values. Yes, indeed. Actually, this is from textbook. A and B values are there. Capital A values are there. And then we have two choices, capital B1 or capital B2. If you take capital B1, then we have larger C value. And if you take capital B2, we're going to get smaller C value. You have ambiguous case. We may have two answers. In some situation, we may not even have an answer at all. Same situation, small and small b are given, and capital A is given. Identical situation. However, if you do the same thing here, same equation, same type, turns out sine of capital B is 1 point something, so that exceeds 1. And that's impossible because sine is always bouncing between positive 1 and negative 1. Sine value cannot exceed 1. That's a contradiction. What does that mean? This kind of triangle doesn't exist. Impossible. So the first case, if you know all the angles, all three angles and a side, you can always determine your triangle uniquely, and the law of sine works out beautifully. All the application problems we are going to consider in this course will be based upon that. The other cases are ambiguous. Sometimes it works, sometimes we have two solutions, sometimes no solutions, kind of like that. Now, do we have enough time to discuss the proof? Looks like we do not have enough time to discuss the proof, so we'll have to postpone the proof of the law of sines to the next video. In the next video, we're going to do some applications. At the very end, we're going to do the proof.